right. So, all right, maybe let's get started. So as you can see, this is our three-stage pipeline for making a puppy, right, or cat. And on the other side, we have single issue in all the execution. If your pipeline is blocked by any stage, then all of the subsequent operations cannot proceed. So they have to crash over there. And a bit of review about branch prediction. This is for the previous assignment. I know when it comes to GHR, then if you want to put everything in the table, it's going to take a lot of effort. So instead, the way I prefer to do it is I would just consider the branch result as a bunch of binary numbers, and then imagine that I have a sliding window of whatever number of bits of the GHR, and then I'll identify all the subsequences in the actual branch results, and then figure out what is the next result that I should predict. Right, based on this kind of sliding window of 4 bits, essentially, as you can see over here, all of these 4-bit patterns in the GHR are different. And therefore, eventually the GHR, the counter will learn the correct prediction. It's going to make 100% accurate prediction. All right, so the more complex question would be, give you a particular branch result and that sequence, how many bits do you need to get perfect accuracy? Right, if you do the table method, you need to try a few GHR widths, 4, 7, 3, 2, etc., right, until you find the right answer. But with this sliding window method, you just don't have to enumerate all those complex branch result, actual result, correct or not, all of those things. You can just analyze the accuracy based on if these subsequences are distinct. All right. So based on this analysis, essentially we see that for all of these different 4-bit patterns, the counter will eventually learn the correct prediction, and it will make perfect predictions. But that's not the end of this question. We need to 4-bit works, so we need to try 3 bits, right? Again, 3-bit, just enumerate all the 3-bit subsequences, 010, 100, 001, etc. Right? These are the 3-bit subsequences from the actual branch results. And as you can see, again, all of these sequences are distinct. So again, the correct prediction, the one after the error, will be learned, and the predictor will make that correct prediction for all the subsequent iterations. All right, so 4-bit works, 3-bit works, we need to go to 2-bit, and again, examine all of these subsequences. And at this point, we are observing some conflicts, right? So, when you see a subsequence of 0, 1, you could really be in 2 parts of the branch sequence. You could be like over here, right? At the very beginning of this sequence, right? You see 0, 1, and then you should predict the 0. But you could also be over here, seeing these 2 0 1s, you should predict a 1. And based on the 2-bit history, right, the 2-bit GHR value, there's no way you can tell whether you're looking at the first 2 bits in that repeating sequence or the middle 0, 1 in this sequence, right? And again, they happen at equal frequency, so it's going to drag your predictor towards prediction 0, 0 and 1, 1, 0, 0, 1, 1 repetitively, right? So there's no way you can settle down to make the correct prediction. So the only thing you can tell from this method is whether you can make perfect prediction or not. You cannot really calculate accuracy. Accuracy still depends on the initial state, right? But again, you can still use this method and also considering the initial warm-up stage, all of the subsequences from that part, and to compute accuracy. So essentially, a small trick if you don't want to use the table method, if you want to, save yourself a bit of time. Yep. Mm-hmm. Eventually, it will always be perfect. So actually, right now, we are repeating 1, 2, 3, 4, 5, 6, 7 bits, right, in the sequence. So 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1. That's 7-bit pattern, right? So for this sequence, if you have a 6-bit predictor and -1, you can always make perfect prediction. The reason is because with n-1 bits, you can tell exactly where you are in that sequence. Except for one corner case, when you have all zeros or all ones, you cannot really tell, but it doesn't really matter. Yes, so 7-bit is more than enough, 6-bit is definitely sufficient, and anything fewer than that requires a more careful analysis. All right. So yeah, I'm glad I only spent 5 minutes on branch prediction because I have quite a few slides on data flow graph. So my take on data flow graph is this is a very useful method to analyze program behavior, right? Rather than the pipeline diagram. The pipeline diagram would be very messy if you consider out-of-order execution, different number of stages, and more than one cycle latency, all of these things. It's going to be tremendously complicated. But data flow graph is a lot easier. Right? So as you remember, data flow graph looks something like this, right? Each node is an operation. It's like an assembly code instruction, right? And then we draw dependencies as arrows. And based on this data flow graph, and together with some other constraints from the processor specification, we can schedule each node at a particular cycle. We can bind each operation to a particular resource. And then that gives you a valid program execution sequence. So, the question is, we need to identify some constraints from the question body, right? Or from a particular processor specification. What are the constraints that are relevant for scheduling the data flow graph? Right? What kind of constraints am I talking about? Any idea? Anyone has some idea? Like, what kind of constraints do I need to consider when it comes to scheduling a data flow graph? Yeah, other than the dependency.
Maybe like you can only run 5 ALU.
5 ALU, yeah, the number of resources.
Or yeah, resources.
Right, like how many ALUs, how many memory, how many branch, even IF and ID, right? How many instructions can you fetch or issue in each cycle? What else? I know on the surface it's the number of resources, right? That's like the resource constraint. But let me show you a few more constraints. You actually need to consider all of these constraints when it comes to scheduling a data flow graph. If you miss any single piece, you will not be able to successfully schedule it. Each of them is equally important. So we just mentioned resource constraint, right? How many instructions can we put in each pipeline stage? And also latency constraint. Well, this is not just dependency, but also how many cycles each operation takes, right? Memory typically takes 4 cycles if it's a cache hit, and then ALU 1 cycle, branch 1 cycle, right? These are all some critical information you need to grab from the processor specification or from the question body. And also decode constraints, right? Even for those instructions that do not have any prior dependency, you cannot just put them at the very beginning, right? You need to fetch them 2 at a time each cycle. So we're still fetching in order, right? So this decode constraint is also quite critical. And also branch prediction, right? Right now we have always assumed that we have a perfect branch predictor, perfect prediction accuracy, and a perfect branch target buffer, right? So we don't have to worry too much about branch prediction. But if we do not have a perfect predictor, we might need to sometimes flush my pipeline, remove some of the calculated result in the buffer, and then restart on the correct target. And finally, registry naming, right? These are all some terms you're quite familiar with, but keep in mind, each of them will play a role when it comes to scheduling the data flow graph. So if we support registry naming, that is more like the conventional case. Then you only need to worry about the true dependency, read after write. Otherwise, you need to worry about all of these true and false dependencies. If you want to ask why, I can explain, but it's going to take a while, so I'm just going to skip it. But if you think for a little while, you'll figure it out. All right, and then based on the data flow graph and all of these constraints, right, you can finally schedule the data flow graph. All right, so I have a random example. This is probably like I took a few pieces from the assignment, a few pieces from the lecture, and just randomly put them together. This is not a meaningful program, right? But probably it serves our goal pretty well. Again, right, we need to identify dependency, essentially draw the data flow graph, right? Nodes and arrows. And then right now I'm defining the other constraints. We have 2 issue, 2 ALU, 1 branch, 1 memory, right? We have the latency for each instruction is specified over there. Perfect branch prediction, unlimited registry name, right? Pretty typical assumption. This is not exactly the same as the assignment because I have 2 ALUs, but in general, it's the same kind of setup. All right. And, when you look at any question, you need to grab this information from the write-up. All right, so the first thing we want to do is, based on the code, we want to draw the data flow graph, right? So, let's slow down a little bit over here and let's just, follow through the code a little bit, right? So what is the first dependency, right? Give me a few dependencies.
3 depends on 1.
Yeah, 3 depends on 1 on RDX.
Yes.
That is my first animation, so I'm just gonna make it show up.
It also depends on 2.
Right? And this pattern repeats for all the subsequent iterations. Right. What else?
It also depends on 2. 3
depends on 2, yes, on RDI, right? So 2 updates RDI, or 2 writes to RDI, 3 reads from RDI.
That's right.
And what else?
5 depends on 3.
5 depends on 3, yes. So.
And 6 depends on 5.
6 depends on 5, yes. 6 depends on 5 through the 0 flag register, right? Whenever we do a comparison, it's going to set the particular register, and then jump is going to check that register. But in addition to that, there's another one from 4 to 7, right? Like, this cross iteration dependency, right? We shouldn't just look at one iteration. We should also look at, adjacent iterations. So 5 dependencies. A few things I want to put a note on. One thing is, be familiar with the source and destination register of each type of instruction, right? I'm not sure, how much I've seen this assembly writing in 142L, probably a little bit, right? Or more than a little bit. So you must be more familiar with the assembly code than me. Sometimes I don't really know what the instruction means. I need to look it up from the manual. And also, pay attention to the type of each instruction. Like, for example, move Q, right? It's moving something from the memory, specified by the parentheses into a register. And Leo, well, even though we also have a parentheses over there, this is not a memory access instruction, right? This is like an instruction that only uses ALU. Essentially a subtraction, but with different source and destination register. All right. So, the source, destination, and also the type, or, whether it's ALU or memory kind of instruction. All right. And then also be aware of the intra-iteration dependency and also inter-iteration dependency, right? Like, 4 to 7, this kind of inter-iteration dependency, we might, some people might easily miss it. And then the dependency pattern will likely repeat across multiple iterations, right? Essentially, you just find the patterns through iteration 1, or maybe a little bit of iteration 2, and then you can just copy down this pattern for all the subsequent iterations. And right now, I'm only showing the true dependency, right? And that is because I know I have unlimited register renaming support, right? So I only need to worry about true dependency, right? Some of these, the way you handle data flow graph depends on the processor specification, right? And what we allow on the processor. All right. So let's just draw the flow graph a little bit. 3 depends on 1 on RDX. 3 depends on 2 on RDI. 4 doesn't depend on any previous instructions. 5 depends on 3. 6, the branch depends on the comparison result. And then 7, the beginning of next iteration, depends on 4. Right? And I like to annotate the kind of dependent register on the side just to make sure that these are actually read after write. All right. And again, right, based on one of the previous rule, you can just repeat this pattern for all the subsequent iterations. So this is iteration 1, and then repeat the same pattern, iteration 2, repeat the same pattern, iteration 3. Okay. And this diagram is what I call the unscheduled data flow graph, right? I'm just drawing the dependency. Well, I didn't include anything else. I didn't include the cycle. I didn't include the resource limitation. Right? I can draw the unscheduled data flow graph based solely on the code and a bit of specification like register support, like register renaming support, right? But mostly on the program, on the code. And then the next thing I like to put in the data flow graph is latency, right? This will be a critical piece of information when it comes to scheduling, right? Like, what is a memory instruction? So I know anything that depends on it, like 3, cannot start until 4 cycles after 1 starts, right? So 1 started at cycle 1, 3 can only start at cycle 4. 1, 2, 3, 4, cycle 5, right? Plus 4 cycles. So, by keep a note of this information, the data flow graph, very quickly, I can forget about the assembly code. I'm able to do all the scheduling based solely on the data flow graph. That is my goal. I don't want to look at the assembly code. And then the next information that I can find from the code is the resource type, right? Each instruction or each operation is using a different type of resource. Some of them are using the memory, like this one with a green edge. The one with the red edge are ALU operations. 6, 12, 18, those are branches. So they're using the branch unit. All right. So by this point, right, what I already have from these several steps, I have a data flow graph, an unscheduled data flow graph, but I already considered the loop iterations, right? I'm I'm putting a slightly thicker border on this, the first instruction in each iteration, so that I can tell, where I go from iteration 1 to iteration 2. And also those are the only memory access instruction in this program. So I'm putting a special note for it. The data flow graph has also contained the latency, right? Those numbers on each edge, and also the resource type, the color of each edge. And these are all the information that we can collect from the assembly code. Therefore, you can forget about the assembly code at this point, right? Just focus on this annotated data flow graph and do scheduling. Right? Isn't that pretty cool? All right. And then when it comes to do the actual scheduling and binding, we need to consider the machine specification, right? How many ALUs, what is the issue with, and all of those factors. All right, scheduling. Scheduling, this is the hard part, right? DFG, the data flow graph, doesn't solve all the issues. You still need to do the manual scheduling. You go through, multiple iteration, one iteration at a time, and then evaluate dependency, make sure to handle the latency, and put everything under the resource constraint, right? Those all go into the scheduling and binding part. All right. There's many different ways you can illustrate the scheduling process. This is actually the way I preferred, the more free-formed way. If an instruction takes 4 cycles, like the memory access instruction, I just draw a larger bubble, right? A larger circle. And therefore, 3 has to come after the end of operation 1. Right? And then I'm using different colors for different resources, like 3, 1, and 7. They are mapped into the same memory unit. I only have 1, so those 2 must be mapped into the same memory unit. And all of these red instructions are using the ALU. And there's an orange instruction which is also using the ALU. I'm assuming that I have 2 ALUs, right? So yeah, which means I can execute 2 ALU operations in the same cycle, but they must be mapped to 2 different ALU resources, right? You cannot use 1 ALU unit for 2 instructions in 1 cycle. You can use 2 ALU units for 2 instructions in the same cycle. All right. But I also like the way Professor illustrates it in lecture, the more resource-centric graph, right? These 2 are really illustrating the same thing, but just, with different reorganization, right? In this professor's diagram, we have a bunch of instructions on the left, right? So we're fetching 2 instructions over there. They're illustrated on the instruction queue. And then we have actually a few columns for different resources, right? If we have 1 memory, 1 ALU, 1 branch, then we're going to have 1 column for each of these resources. I will actually follow Professor's diagram in the subsequent slides with a bit of tweaks so that I can more easily type them on paper. All right. So remember, we have instruction queue, and then 1 column for each resource. So this is how I'm illustrating it. I have instruction queue. I have 1 column for each resource. Right? ALU1 and ALU2, those are not the 2 stages of the ALU. Those are 2 independent resources. Right? That is based on my question specification. I have 2 ALUs. So I'm illustrating 2 columns for ALU, and at any cycle, I can put 2 operations on these 2 ALU units and let them run in parallel. All right. And based on this skeleton, then you can draw those bubbles and arrows, right? Essentially, draw the scheduled data flow graph, or you can just illustrate them by numbers and ignore the arrows. That's what I'm doing right here, because there are a lot of arrows. If I were to also include the arrows and nodes, it's going to be a very messy graph, and it's very hard to follow. All right. So coming back to this table, first, we're going to create the columns based on the resource availability. All right. And this is essentially the same table, but the same kind of diagram, but in a more tabular format, right? Easier to type on paper. And then I know that this is a 2-issue processor. So each cycle, I'm bringing in 2 instructions into my instruction queue. All right, and those are fetched in order. And actually, I also have some indices, right? These are, similar to cycle, but those are not real cycles. Because, if we were to do it in the pipeline diagram, then we need 1 cycle for fetch, 1 cycle for decode, 1 cycle for reorder, right? So my cycle 1 in this table is actually cycle 3 in a real processor. There were 2 cycles before it to fetch and decode. And right now, the instruction queue is like the reorder buffer, right? So, quite subtle point, but it doesn't really matter when it comes to analyzing the steady state CPI. All right. So, because I know I'm going to fetch 2 instructions in every cycle, and my reorder buffer, has an unlimited site, I don't need to worry about having too many instructions waiting there. So I can always fetch 2 instructions in each cycle. I can just fully populate that first column. All right. And then we're going to do some real scheduling. All right. So in cycle 1, I put 1 and 2 into the instruction queue. So cycle 2, they can go into execution, right? There's no dependency between the 2. They do not depend on any previous operations. So they can go into cycle 2, right? And I'm putting them in different resources. Okay. And then in the next cycle, right, 3 and 4 are waiting in the instruction queue. But I can only put 4 into the pipeline, right? Because 3 is waiting for the result of 1. 1 is not going to finish until 4 cycles afterwards. So you can now start 3 on cycle 3, but you can start operation 4, right? 4 doesn't have any dependency. As you see, right, on that memory column, I'm putting a small 1 over there, right? Just indicate that the memory resource is still being occupied by operation 1. And don't put any other operation in the memory, even if there's no dependency. Right now, there's probably some resource conflict, right? So if the resource is occupied, I cannot put any other instruction into the same memory. All right, and in the next cycle, 5 and 6 will be decoded, but none of them can be put into the pipeline, right? So these 2 new instructions, 5 and 6, they're still waiting for 3. 3 is still waiting for 1, so they're not ready to execute. So right now, 3, 5, 6 essentially like waiting in the reorder buffer, and they're waiting for 1 to complete. Next cycle, I'm decoding 7 and 8, right? And 7, well, 7 depends on 4. 4 is already completed, but right, I still cannot bring 7 into the pipeline because 7 is a memory instruction. And memory, in this parentheses 1 is taken by operation 1, right? And 8 doesn't have any dependency. I do have available resource, so I can put 8 into the pipeline. All right, next cycle, 9 and 10 are decoded. 9 depends on 7, 7 depends on 4, depends on resource of 1, so I cannot execute 9, but I can execute 10. All right. So at this point, 1 just completes its execution, and it frees up the resource of the memory, so I can put another instruction into the memory, right? So at this point, I put 7 into the memory. I guess some of you might probably already see it. This is essentially the same as the kind of bubble diagram, right, that we use for the scheduled DFG, right? You can just think of each bolded letter or bolded number as one node, and then dependency will be illustrated by some additional arrows. All right, next cycle, 11, 12 are decoded. They cannot be executed because they depend on 9. 9 hasn't started. But what about some other instructions waiting in the pipeline, sorry, in the reorder buffer? Well, 5 was waiting for 3 and 3 just completed. So I can put 5 into the ALU for execution. Right, and 7 is still on its second cycle of using the memory. And the next cycle, 13 and 14, 13 still waiting for the resource. 14 is ready to run. So 13 and 14 goes into, 14 goes into the pipeline. And then 6, right, after the completion of 5, I can also bring 6 into the branch evaluation unit. Next cycle, what about these new instructions, 15 and 16? Well, 15 is waiting for 13, so I can now run it. 16 doesn't have any dependency, and I have an ALU available to write 16. Right, 7 is still running in the memory. And next cycle, well, there are a couple of things, right? 7 completes its 4 cycles. So I can bring the next memory access instruction, which is 13, into the execution stage, into the memory. And then at the same time, I just completed 7. So the one that depends on date of 7, which is 9, can also enter its execution. And then, well, actually, I need a bigger graph because I'm already running out of operations. So I'm expanding the graph a little bit, right? Just repeating that sequence for 2 additional iterations. And then 11 and 12, well, 11 is the one that comes right after 9. 20 is the newly fetched instruction, newly decoded instruction. So both of them can enter execution. And I'm going to accelerate a little bit. And then 21, between 21 and 22, 21 is waiting for the data. 22 is ready to execute. Right, 12 is the branch that comes after 11. And you just repeat this pattern for a few additional cycles. And then the graph will be complete. Right, I have a pretty completed graph at this point. This is for 1, 2, 3, 4, 5, 6. For 5.5 iterations, right? I'm illustrating all the execution results of the DFG. All right, a lot of things are happening over here. I am a little bit overwhelmed, and I know you must also be overwhelmed by all of these numbers flowing around. Right? There's some patterns emerging, but there are also some not so elegant access patterns. So let me try to break it up a little bit. All right. So now it's time to recognize a pattern, right? When you look at the data flow graph, you see you have this chain of 3 operations, right? Just hanging on the side. There's nothing that depends on them. So once you execute 3, then you can execute 5 on the next cycle, 6 on the cycle after, right? So once you run 9, next cycle will be 11, and then the next one will be 12. So there's a bit of just very smooth flow between every group of 3 operations, right? 3, 5, 6, right? They're executed in 3 consecutive cycles. 9, 11, 12, 3 consecutive cycles, right? Same goes for every this vertical group of 3 operations, right? These are like one kind of pattern that you should recognize from the scheduled DFG, right? The next pattern is for these nodes, 2 and 4, 8 and 10, right? These are the nodes sitting on the almost like the top level. They don't have any prior dependency, right? So whenever they are fetched and decoded, they can enter execution if I have enough resources, right? They do not depend on the result of any other operation. So there's no data dependency for these operations, but there could be some decode constraint, right? We need to wait for them to be decoded to start execution, and also there could be some resource constraint. But right now with 2 ALUs, my resources is more than enough for this program. So we don't need to worry that much about resource constraint. And it turns out that, if you look at the time between when they are decoded, like when they enter the reorder buffer, and when they get executed, it's just off by 1 cycle, right? Right after decode, they will go into execution. Right? Like even though they're sitting at different columns, that's really because at the warm-up stage, things are not that stable, right? But really, the important thing is that they would always enter execution right after being decoded. All right. So what are the remaining operations? I show you that chain of 3 and also this the top level operation. What are the remaining operations? What are the operations that we have not analyzed?
Memory.
Yeah, the memory, right? The kind of bolded nodes sitting on the diagonal. So for the remaining memory operations, right? You see, each of them is taking 4 cycles. Each of them is held back by the resource constraint, right? You only have 1 memory. And 7 was actually waiting for the resource to be freed up by 1. 13 is waiting for 7 to complete on the memory so they can go to the memory. 19 is again waiting for the memory resource from 13, right? So it's really this resource dependency, or like, what is it called? There's a kind of conflict that happens on resource, right? Like if 2 operations are looking to get using the same resource, what kind of conflict do we call it? Structural conflict. Is this structural conflict or? Oh, structural hazard, exactly. Yes, this is essentially, this represents a structural hazard, right? If you allow 7 to enter execution while 1 is still using the memory. But, we are delaying the 7 until the resource is freed up. So there's no hazard over here. But as you can see, these memory instructions, they do sit on the critical path, right? Everything else is waiting for them. So for example, as we're executing the memory instruction of 1, I cannot run any of the 3, 5, 6, right? This chain of 3 cannot run. They're waiting for 1. So once operation 1 completes, the 3, 5, 6, right, they will be executed right away. So really, they're just waiting for that memory operation to complete. And then because I have a lot of ALUs and I have enough branch evaluation units, I don't need to worry about resource constraint over there. They're just waiting for 1. And 7 is also just waiting for 1, right, on the resource. And therefore, this sequence of memory access instructions becomes a critical path limiting CPI. So what is the CPI? I don't want to show this animation, but my computer is stuck. What is the CPI? Don't look at it. What is the CPI for the code? Okay, I'm hiding a part of the animation. What is the CPI? Well, yeah. 7 divided by 4. 4 divided by 7. Okay. Where did you get 4?
So you look at the critical path, right?
Mm-hmm.
The critical path kind of denotes a block.
Yes.
And stand out, you see it'll count 7 instructions in that block.
Okay, so 4 cycles because we're spending 4 cycles on each iteration, right? So 1 is the beginning of 1 iteration, 7 is the beginning of the second iteration. So we're spending 4 cycles in iteration 1. Well, not technically, but roughly we're spending 4 cycles in iteration 1. We're spending 4 cycles in every iteration. But there are 6 instructions in each iteration, 1 to 6, right? There are only 6 instructions. 7 is already the first instruction of the next iteration. So every 4 cycles, I can essentially complete 6 instructions, right? So cycles per instructions, 4 cycles per 6 instructions is my CPI.
But you're not done after getting the memory though. Don't you need I don't understand. Don't you need 2 more cycles or 3? Don't you need 3 more cycles to do 3, 5, and 6 after you get 1?
Okay, so the thing is, right now the kind of CPI we're calculating is called steady state CPI, okay, which means the rate at which you can bring in instructions into your pipeline and also complete the execution. The latency of each individual operation doesn't matter.
Okay.
Right, so when it comes to like additional 3 cycles, I think you're thinking about the latency, right? The latency of that memory instruction. But here we just care about, if I don't care about latency, but rather I care about the rate at which I can execute the loop, right? The latency of individual iteration doesn't matter. It could be like each iteration take 100 cycles, but I can still just finish one iteration in 4 cycles and bring in a new iteration if every 4 cycles. Right? Whenever it comes to terms like throughput, well, this is essentially throughput. Throughput and latency are 2 different concepts, right? Latency is how long it takes to complete each individual instruction, or maybe how long it takes to complete one iteration, right? But throughput is, it's assuming that things can be pretty nicely pipelined, and CPI represents the pipeline speed, the speed at which I can run my pipeline. The pipeline is a pipeline of bringing in a new iteration and then completing a prior iteration. All right, so that's a lot of numbers, right, in the past several slides. So let me rewind a little bit. All right, so remember, we were just, doing it line by line to schedule the data flow graph, right? And also considering, when we're doing scheduling, we're considering the resource constraint, data dependency, and latency, and the, a number of other factors. And then over here, right, this is for the completed graph. I'm trying to analyze what is the pattern for each group of operation, right? And I divide them into 3 groups, the chain of 3, the top level, and also the diagonal memory, right? They exhibit 3 different patterns. And these patterns, well, based on this pattern analysis, you can conclude that, at this point, I already see enough details to calculate the average CPI. I know it's going to be the same pattern for all the remaining iterations, right? But, the thing is, the scheduled data flow graph doesn't necessarily look regular, right? You don't necessarily have the regular pattern repeating over there because different groups of operations are aligned differently, right? The chain of 3 is aligned with the memory access, right? The memory access is aligned every 4 cycles, right? So those 2 will be pretty much aligned. But for the remaining ALU2, well, those operations that go to, the top level, the 2, 4, 8, 10, 14, 16, they are actually aligned with instruction fetch and decode, right? So they happen a little bit earlier than the execution of the other instructions. So if you look at the overall picture, it may not look very regular, but if you divide it up into these several groups, you will see each group exhibits a regular pattern. Now, whenever you see the regular pattern, you can stop the analysis. I don't think you even need 5 iterations. You can probably do it in 2, 3 iterations, right? If you know what kind of pattern you're looking for. All right. So remember, I told you something like this at the beginning, right? These are all the things that you need to pay attention to when it comes to program analysis or DFG scheduling, right? So let me also, remind you when we use each piece of information. So when did we identify the dependency? Right? You still remember?
From the assembly code in the very beginning.
Yeah, at the very beginning, when we derived the unscheduled DFG, right, we were analyzing the dependency in the assembly code. What about resource constraint, right? When does it play a role in the DFG?
That's given in the problem.
That is given in the problems. Yeah. So when did we apply that piece of information to schedule the DFG?
When you transfer from, what was that graph again? Transfer from the previous graph to the later one.
It's from the unscheduled to the scheduled one.
Yeah, thank you.
Yes. Okay, so maybe let me point out 2 examples, right? So, well, actually, we use pretty much dependency, resource, and latency constraint to schedule every operation, right? And just, selecting 2 particular examples. One example is between 1 and 7. They're scheduled back to back because of resource constraint, not because of data dependency, right? This is only because of resource constraint. They're competing for that one memory unit, right? Because we have one memory unit, but multiple operations using the memory unit, they have to be scheduled one after another. And also because we have two ALU units, that allows us to schedule 3 and 10 in the same cycle. So if we only have one ALU unit, 3 and 10 cannot go into the same cycle. If we have two memory units, 1, 7 can run in parallel. Right? That's where resource constraint is critical for the scheduling of DFG. All right. What about latency constraint? Well, latency pretty much goes together with dependency, right? If latency is 1, the next instruction have to go to the next cycle. If latency is 4, it has to be 4 cycles after the dependent instruction, right? So, a random example would be between 7 and 9. So if you look at the DFG, 7 and 9, they need to be 4 cycles apart, right? So 9 is already ready when, it's already decoded way before it, but, we cannot let it execute until 7 completes, right? This is where dependency together with latency plays a role in the scheduling. All right, what about decode constraint? Right, remember, we need to decode before we can start the execution.
So you worry about that when you're filling out this table.
Yes. Do you have a more specific example, like which particular cell?
Instruction queue.
Yes. So we're looking at the instruction queue to determine what can be, what we can bring into execution, right? So again, pretty random example. 20 doesn't have any dependency, right? So if there's no constraint on the instruction queue, if we have an unlimited size instruction queue, we have an unlimited issue width, then we could have run 20 much earlier. But because we have a two-way or two-issue processor, and we are fetching these instructions in order, we have to delay the execution of 20 until we have fetched it in the cycle before. All right, but really, every instruction follows this rule, right? They need to wait for it itself to be decoded before execution. Branch prediction. That's the next part. Branch prediction. This is a little bit subtle, right? Where did we take advantage of the perfect branch predictor and also the perfect BTB, branch target buffer? Or in other words, what would happen if we do not have branch prediction?
Oh, okay.
Right? Sometimes you take these points for granted, but really these are based on the question definition. If I give you a different definition without branch prediction, different latency or different decode constraints, everything will change.
Then 7 would depend on 6.
7 depends on 6, exactly, right? 6 is the branch. So the next iteration depends on the branch result, right? Without branch prediction, we cannot execute 7 before 6. Or I'm just finding some empty space to draw my animation. 19 depends on 18, right? But because of branch prediction and the target buffer, I can run 19 before 18. And finally, register renaming. Oh, where did we use that, right? Or what will happen if I do not have register renaming? Yeah, I can bring up one of the previous slides. Not this one. This one, right? So with register renaming, you only care about true dependency, right? Otherwise, you need to care about all the false dependency as well, right? And there are a lot of false dependency in this program, and don't worry about this particular example I'm illustrating, right? But this is an example of write after read dependency. Typically, this is a false dependency, and we don't have to worry about it because the question says we have unlimited registry naming capability, right? If we do not have this capability, or if we do not have registry naming, we also need to consider additional constraints in the original unscheduled data flow graph to include all the false dependency. All right. So, each of these specifications will affect your decision. All right. So, well, 4 minutes to go. Very small practice, right? What if, for the same program, the same data flow graph, what will happen if I have unlimited resources? Unlimited, issue with unlimited resources, right?
I want to guess is 0.5 for the CPI.
0.5. What is your formula?
Because now the critical path is only 3. Because 1 and 7 can run in parallel.
1 and 7 can run in parallel. Yes.
So
what is the critical path? Right, essentially, with unlimited resources, we can just run things as early as possible. Right? We don't need to wait for fetch. We don't need to wait for resource. We still need to wait for dependency, but as you can see, this diagram is really composed of a few subtrees. Right? There's like no real connection between different iterations.
is it 1/6?
1/6. 1 cycles per 6 instructions.
Yeah.
Well, remember, right? In the previous example, it's 4 cycles for 6 instructions, right? Over here, actually, we have an unlimited CPI, or like almost 0 CPI, because we can. I realize I made an error on this slide. So because we can essentially schedule everything in parallel, right? Like I can use 1, 2, 3, 4. I can use like 6 ALUs, 6 memories, right? They can all run in parallel. So really, like this whole program, regardless of number of iterations, has the same amount of latency. It's always, like 8 cycles. That is the overall latency from 4 to 12. But that number also doesn't really matter. But with a fixed number of cycles, you can run as many iterations as you want. Right? Like these different subtrees have no dependency, so they can all run in parallel. So really, because we have infinite iterations, and 8 cycles, it doesn't matter whether it's 8 or 4 or 1, depending on how you count it. But CPI is almost 0, right? Cycle per instruction, you take almost no time for each iteration. It doesn't scale at all with your number of iterations, right? So this is if someone actually wrote this program, has great LP, instruction level parallelism. So this guy, the programmer, must have excelled in CSE 142L. Right? And this is not infinity. This is more like 0, right? CPI of nearly 0. Some number, a constant number divided by infinity. All right. So that's the end of the session. Just a bit of clarification about assignment 2. Assignment 4. These 2 instructions, move Q and add Q. The first 2, move Q and add Q. These are memory instructions. This one is actually reading from the memory, and this one is taking the registry result and write it and do an addition and then write it to the memory, right? So technically, the second instruction will take like a memory and then ALU and then another memory. But we just, for simplicity, assume that if an instruction uses memory at all, it takes 4 cycles, right? Don't worry about like the more complex pipeline stages. All right, and everything else will take 1 cycle. So, all right. That's all for today. Again, we have 1 audience on Zoom. Thank you, Blake, for joining us. And I'll stop the meeting and stop recording.